Good morning, good afternoon, and good evening, everybody, and welcome back to VGEM 2021. So this morning, I hope everyone's had a wonderful meeting so far, and we're going to move directly over to our student moderators, Longzhi and Aaron, to introduce our first speaker.
Hello, my name is Aaron Flavius West. I'm a PhD candidate at the University of Minnesota. I will be moderating the Q&A portion of this talk.
Hello, everyone. My name is Longzhi. I'm a PhD student from Boston University, and I'll be introducing the speaker of this inner magnetosphere session. And without further ado, let's get started. Today's inner magnetosphere plenary speaker is Dr. Mary Kay Hudson. Dr. Hudson received her bachelor and PhD degrees in physics at University of California, Los Angeles. After 10 years at Space Science Lab at UC Berkeley, she joined the Physics and Astronomy Department at Dartmouth College in 1984, where she has supervised many GEM graduates and postdocs. She is currently also a senior research associate at the NCAR High Altitude Observatory. She's an active member of the heliophysics community and was the GEM steering committee chair from 2000 until 2003. She was awarded the James A. Vallon Space Environment Award in 2012 and the AGU Fleming Medal in 2017. Dr. Hudson's research interests include space weather, radiation belt dynamic of the Earth, the interaction between the Earth's magnetosphere and solar wind, and solar cosmic rays. And let's welcome Dr. Hudson.
Okay, thank you very much. All right, I'm going to, try sharing my screen here. Here we go. There, and there. Okay, and now to full screen mode, hopefully. Okay, good, thank you. Well, it's really a pleasure to speak to this audience again. I wish we could all be in Snowmass for this anniversary, where it all started. So I am going to, I've been asked to summarize briefly the GEM Intermagnetosphere Storms campaign. And again, I'd like to thank the organizers for this invitation. This was the third campaign in GEM, and planning for it began at the June 96-97 Snowmass meetings. George Sisko, whose name should be on this slide, was an instigator in our conversations about starting the new campaign. And it became a fully funded NSF campaign by the June 99 workshop. I served as the first campaign coordinator, followed by Anthony Chen. And at the bottom here, you see the three initial working groups and their coordinators. We called them working groups then instead of focus groups, but they served much the same function. And very early on, we consolidated down to two working groups with the overlap of the ring current in working groups 1 and 2, and we consolidated 2 and 3 into the radiation belt working group. But about halfway through the campaign, we added a ULF wave working group, which became an obvious need for our studies. The UCLA GEM Wiki turns out to be a real goldmine of information about the history of GEM. I had to go back there myself to recall some of it. And I'll give you at the very end some links to this and a few other references. Ray Greenwald helped me summarize the initial years of the Intermagnetosphere Storm campaign in the wiki. And then there's a very nice introductory article by Mike Lamone in 2006 JGR, where there was a special section on the Intermagnetosphere Storms Assessment Challenge. The initial events chosen for study were these storm intervals you see over here on the right. And they were very much influenced by the International Solar Terrestrial Physics Program of the 90s, NASA program, which included the WIND spacecraft at L1, Polar, and Geotail. It did not include the Equator satellite that was originally planned for the intermagnetosphere due to budget constraints. However, the NASA program, this NASA program did fund development of MHD global simulation models, at least 2 of them that are currently used by our community. And our next speaker, Jimmy Raeder, I'm sure will be discussing that. The NASA ISTP program also funded a significant expansion of ground-based coherent radars. So the Super Darn network, which was really useful for the campaign, was instituted with funding from NASA. In addition, there were a number of other spacecraft data assets used, the LANL and NOAA geosynchronous spacecraft, and the NASA SAMPEX small explorer spacecraft. I'll show you some data from that on the next slide, I think. The NOAA POSE and DMSP were other low altitude polar orbit spacecraft used. And then midway through the campaign, NASA launched the IMAG satellite, which provided really a revolutionary view of the plasmasphere and ring current midway through the campaign. And then finally, last but not least at all, NSF provided direct funding for ground-based instrumentation and also for model development. Okay, next slide. Next slide over here. Let me get my next slide going. I'm on a temporary freeze of my screen. Oh dear. I was doing so well over there. Maybe now we'll be okay. Okay, good. Whew. Okay, so this is a very nice table that was in Mike Lamone's paper that summarizes characteristics of the intermagnetospheric plasma populations. And it shows you how different they are in their basic characteristics: the plasmasphere, a dense cold population, the ring current, which carries most of the energy in the region, energy density, and then the radiation belt population down at the bottom, which in Mike's table dominates the spacecraft effects. And I'm going to focus on the bottom, the radiation belts, because that was the working group that I was heavily involved with and continue to be involved with. And I hope you'll invite our current GEM chair, Vanya, or former GEM chair, Mike Lamone, back in the future to discuss the other 2 populations. Okay, so I'm going to try to get my laser pointer going over here, which was the whole reason that I asked to be able to drive this. So that will take me just a second here. There we go. Okay. So this is a favorite slide of mine. It's an early version of one that's been that was developed by Shinlin Lee, that takes a long-term view of the outer zone electrons as seen by the low altitude polar orbiting SAMPEX satellite. And so what is plotted here is flux in the 2 to 6 MeV range as a function of L and of time. And at the top, you see the sunspot number in black and weekly average solar wind speed in red. And what you notice here are storms that are causing enhancement in outer zone electron flux during the declining phase from the previous solar maximum. And they are concurrent with significantly increased solar wind velocity. So these are high-speed stream driven storms, so-called co-rotating interaction regions. In the next slide, I'll discuss a little bit about their source back at the sun. During the rise to solar maximum, the storms are more episodic and less regular and are caused by coronal mass ejections. And then the slide captures the decline from the next solar maximum, where again you have an enhancement in the weekly averaged solar wind velocity. And then it trails off to the 2009 solar minimum, where you see a significant decrease in the outer zone electron flux with the declining solar wind driving. You also see this black line, which is the minimum L of the plasma pause. So the plasma sphere on average is relaxing outward at this time of reduced solar wind driving. Okay, so in terms of the solar drivers, The first type of storm that's prevalent at solar maximum is driven by coronal mass ejections. Here's an image from the LASCO white light coronagraph where you see a CME. You see a CME that is the source, in many cases, depending on its location on the sun, of interplanetary shock initiation, which propagates towards Earth and impacts the magnetopause and initiates the CME shock-driven storms. On the right, there's another category then prevalent in the declining phase, where you see these 27-day periodic enhancements in geosynchronous flux in the bottom panel, and they map to the solar rotation of a low latitude coronal hole. So the open magnetic flux from the polar region is now extending down to the equatorial region of the sun and creating high speed flow that is flowing towards the Earth every solar rotation, which in turn is creating these geosynchronous flux enhancements. Okay, and again, every once in a while, my screen is freezing up on me. Okay, there we go. Okay, so now here's the latest version of this slide by Chen, which goes all the way to 2019. Wow, where did can you still see the screen? There we go. Okay, good. So it goes all the way to 2019. And so now it's capturing the second solar maximum during the lifetime of SAMPEX, which lasted until November of 2012. After the launch of Van Allen probes in August 2012. And so Chen and his colleagues have extended this map using the Van Allen probe data, mapped appropriately to compare with the SAMPEX data. And so now the thing I want to notice, and there's a couple of things here. First of all, this most recent solar maximum, as many people are aware, was a mild one compared to its predecessor. And you can see that in the relativistic electron flux. And furthermore, this was a very deep solar minimum in 2009 as compared to the one we just experienced in 2019. And what is the difference between the two? Well, immediately you see that the high-speed streams continued on into the recent solar minimum, but they were much reduced during the 2009 solar minimum. So I'll come back to this point at the end. Okay, so now what is the connection then with solar wind velocity? This is a vintage figure from Paulikas and Blake 1979. Wherein using data from the geosynchronous ATS-6 satellite, they showed the correlation between solar wind flux and geosynchronous flux and solar wind velocity. And this correlation was revisited by Jeff Reeves in a 2011 paper using roughly 20 years of LANO geosynchronous data. He showed that the MEV electron fluxes tend to increase under increased solar wind driving, plotted across the bottom. But the increased fluxes persist at a given level after the solar wind velocity has decreased. And so you get more of a triangular shape distribution. So that's the connection that was already evident in the previous slide of Chen. What is the handoff to the magnetosphere? And so one suggestion that was thoroughly explored, and the reason that we added a ULF wave group to the working group to the campaign, is this correlation that was pointed out by Rostocker in a 1998 paper, wherein you see the rise in ground-based magnetometer power in the millihertz frequency range as seen at a Canadian magnetometer, preceding the rise in greater than 2 MeV flux seen at GOES by about 2 days. And this occurs regularly, one right after another with each solar rotation. Sometimes you have more than one coronal hole on the sun at low latitude at different longitudes, but you see this regular roughly 2-day lag between the rise in the ULF wave power in the magnetosphere and the increase in geosynchronous fluxes. So now then, what is the connection between solar wind velocity and the ULF wave power? So there are two scenarios on this slide. One is direct coupling, and so this is from a paper by Kepko et al., which compares the pressure oscillations at the wind spacecraft, and this is as a function of frequency, and you see these spectral peaks, with oscillations in magnetic field, seen at GOES, where you see the same spectral peaks occurring. And so the implication here is direct solar wind driving of these ULF wave oscillations. Another scenario is convective growth at the magnetopause by Kelvin-Helmholtz instability. So you have shear flow along the magnetopause and in the magnetosheath. And this was proposed early on by Mura and studied by Seth Claude-Pierre et al. And others as another excitation mechanism wherein increased solar wind velocity would increase the ULF wave power in the magnetosphere. Okay, now this is I think the earliest, or one of the earliest, of what became a diagram to describe a new type of mechanism for accelerating electrons associated with increased solar wind driving. So this shows an equatorial plane cut of the magnetosphere, and you see electrons and protons all in black and white back in the day, coming in from the plasma sheet, electrons drifting around to the dawn side, and exciting Whistler mode chorus waves slightly below the electron gyro frequency, which violate conservation of the first adiabatic invariant and can cause acceleration of electrons locally, as opposed to radial transport due to ULF waves. Now this figure took on a life of its own, and here, for example, is a more recent one in a paper by Jeff Reeves, and I think I've embellished it even further. But you see the electrons, which are red here, drifting in from the night side, and they're enhanced during periods of enhanced convection associated with enhanced solar wind driving in red up in the upper left corner. And they excite Whistler mode chorus, and in doing so, this first adiabatic invariant over on the left is no longer conserved. And you can get scattering not only in momentum and energy, or also in pitch angle. And so the Whistler mode chorus can cause loss as well as local acceleration, of the radiation built electrons. This is combined in this figure with the effect of ULF waves. And ULF waves have a frequency comparable to the electron drift period. And so they cause a violation of the third adiabatic invariant, which is the flux inside a drift orbit. And so that results in a random walk, which, given a radial gradient outward towards the plasma sheet, will cause electrons to be transported radially inward. So these are the two competing mechanisms that we talked about yesterday on a rad belt ULF wave panel. Other wave modes appear in this now complicated figure, including His, which is another type of Whistler mode inside the plasmasphere, that's known to be responsible for the slot region, the inner edge of the outer zone electrons, again by pitch angle scattering. And then electromagnetic ion cyclotron waves, which are excited by ions drifting around the dusk side, can also cause loss. All right, so in addition then to that first mechanism of ULF wave acceleration, a lot of work has been done on since the intermagnetosphere storms campaign, when it really took off, on Whistler chorus excited by plasma sheet electrons. And then Whistler His once again contributes to loss inside the plasmasphere. And so this is a somewhat simpler diagram emphasizing the His inside the plasmasphere responsible for loss, chorus outside responsible for both acceleration and loss, depending on the most critically on the energy of the electrons. And an interesting result that came out shortly after the end of the intermagnetosphere storms campaign was this paper by Jacob Bortnick, noting that chorus can be a source mechanism for His inside the plasmasphere. There are other sources, including lightning, ground-based transmitters, and so on. All right, so much for cartoons. So Van Allen probes was launched in 2012, and now it became possible to be more quantitative in testing some of these models. And so one of the first really outstanding tests was done by Richard Thorne and his group of the suggestion of local acceleration. This was a storm that occurred in October 2012, and you see the very strong southward IMF-BZ measured at L1 during this storm. The second panel shows chorus wave power over orbits of the Van Allen probe spacecraft, and so you can see that it was enhanced during this time. But that only gives you the chorus power in the longitude, at the longitude of the Van Allen probes, which was between dawn and noon at this time. And what's needed is the distribution of chorus power over all longitudes. So Richard Thorne and Win Lee contributed significantly to this work, and others in his group began using posed electron precipitation, which is available at different longitudes, as a proxy for radiation, for the existence of chorus at different longitudes. And with that greater information on the distribution of chorus power in longitude, they were able to do a Fokker-Planck calculation at a fixed L, a fixed radial location in pitch angle and momentum, and reproduce the change in the phase space density, which is indicated at 90 degrees here at the top, at different energies. And so if you're at a fixed L, you can have phase space density at a fixed set of energies. And this is the result of their simulation from the Fokker-Planck calculation, which did a very good job of reproducing the significant increase in flux. Notice these are orders of magnitude over here in a matter of just a few hours on the 9th of October, 2012. All right, now, in addition to that type of calculation where you do a momentum pitch angle diffusion calculation at a fixed L, it is also possible to improve upon previous calculations of the effects of Whistler mode His. And this was done in a nice paper by Jean-Francois Ripoll, and also reported by Jeff Reeves, the comparison with data, wherein they did a radial diffusion calculation, but with a time-dependent loss term based on wave observations. So we now had greatly improved wave observations during the Van Allen probes era for improving the model for the Whistler mode His loss. And so up at the top, you see kind of a standard plot of flux versus L value at different energies during quiet and during disturbed times. And down at the bottom, with this Fokker-Planck calculation over here, they computed flux as a function of energy and L. And at quiet times, you see this creation of the slot region. They referred to this as an S-shaped profile. And at disturbed times, that gets filled in, but then recovers over the course of a long interval, a long quiet interval. They took the first half of March 2013 for this study. Okay, now this is one of my favorite cartoons, and I think this is Richard Thorne's, but I don't think it was ever published, and it certainly wasn't in the Nature paper. You have to trim at some point for Nature. And if anyone is aware of where this is published, I'd love to have that reference. But it again summarizes this local acceleration mechanism where you have electrons injected from the plasma sheet, exciting Whistler mode chorus, creating local heating, and creating this peak in phase space density due to the local heating. And then the argument made in this and other papers is that subsequently that local heating gets smoothed out by radial diffusion. So I'd like to show an example of how that picture is, maybe a little bit more complicated. And so this is from the strongest storm of the Van Allen probe era, the March 2015 St. Patrick's Day storm. And these are plots of phase space density at 1,000 MeV per Gauss, so the low energy end of the radiation belt. They're plotted sequential orbits, hours shown in color. And so here you see the initial orbit, which starts out at 5.8 RE, is approximately the same as L star in a quiet magnetosphere. But then when the shock arrives, you have a combination of compression of the magnetosphere and magnetopause loss. And so the next orbit shows that you're starting at L star equals 4 instead of out at 5.8. The really important thing is on the subsequent orbit, you see this peak in phase space density developing. But by the end of 2 days, you have this basically monotonic profile, which is over an order of magnitude higher than the peak in phase space density that you see on the earlier orbits. So that can be a result of both outward radial diffusion, certainly from the peak in phase space density, but also continued inward radial diffusion and inward convective transport of the plasma sheet source population. So what is the story? And we talked about this yesterday on the panel. What is the dominant mechanism here? And I think we came to the conclusion, as many people have, that both are important mechanisms. This is from a paper by Ma et al., which is a 3D diffusion calculation, so including L, pitch angle, and momentum. And across the top, the first 2 panels show the before and after observations of flux as a function of energy on the vertical axis and L on the horizontal axis. And then there's a comparison with simulations turning on different mechanisms. And so here is a simulation only including radial diffusion. Here is a simulation only including chorus local acceleration. And if you compare both of those, they are not as good in comparing with the observations as including both. And so down here on the lower right, both radial diffusion and chorus local acceleration are included, and you see really good agreement, including the L dependence of the profile. If you add His to the calculation, for this particular storm simulation, the agreement was not as good. So there's more loss apparent here due to His than was observed. And that says something about the model that's being used for His. And so in general, we need to improve our models for the wave interaction processes that are affecting the evolution of the radiation belt. Okay, I'm going to come back then quickly here to this nice summary plot by Chen that goes through 2019. I want to compare now the difference between the 2009 solar minimum and the recent one that we just experienced, where high-speed streams persisted into solar minimum because of the presence of low-latitude coronal holes, which essentially vanished by comparison back at the 2009 minimum. So we have this time period really well covered by Van Allen probes. And here from the REPT instrument on Van Allen probes, you see these periodic high-speed streams, and they're really, my laser pointer is drifting to the right, but if you look over to the right, August, September, October 2019, the very end of the mission, you see these 27-day enhancements in the radiation belt electrons due to the high-speed streams. Now, in addition to that, over here, May of 2019, there was a series of 5 coronal mass ejections that were coming from the same active region on the sun. So we even had some CME shocks in 2019, in addition to the persistent high-speed streams. And we had the strongest enhancement, the hardest spectrum, associated with a high-speed stream at the end of September, end of August, beginning of September. And this had not been seen since the very active September 2017 period. So I'll just wrap up by showing you some of the things we can do now with MHD test particle simulations. This is a comparison of test particle simulations of the two storms I just noted. The top one, May 2019, the bottom one, August, September 2019. And plotted once again, like I showed before, our sequential orbits of Van Allen probe over 2 days on the top plot and 4 days on the bottom plot. And the black dots show the results of MHD test particle simulations using LFM for the LFM coupled to the Rice convection model, the Lionfetter-Mowbray code, and using that to push test particles, and then weighting the test particle distributions with the initial radial profile of PSD measured by Van Allen probes and updating it at the outer boundary apogee of Van Allen probes over time, every time Van Allen probes went out to apogee. And the black dots correspond to 34 hours, which is greenish on this plot. And it does a pretty good job of capturing the inward transport that was seen for this event. And over here at 5,000 MeV per Gauss, these are two different first invariants. You see it does a pretty good job of capturing the drop in flux at high L values associated with magnetopause losses. Now, down here at the bottom, this is a longer simulation. So this was done with the new Gamera RCM code over 4 days to calculate the MHD fields into which we sprinkled the test particles and weighted them with phase space density to produce this comparison. And so now the comparison should be made with the yellow curves at the end of 4 days. And it does a good job at capturing, again, the radial profile at the end of this 4-day period. But what you see it lacks, that is particularly evident when you run for 4 days for this event, there is a peak in phase space density that has occurred, very likely due to local heating, which is not contained in our model. So one thing you can do with the MHD test particle simulations is see what part of storms are well captured by radial transport. And certainly the main phase of CME shock-driven storms has been shown for many storm studies to capture the magnetopause loss. And you also capture inward radial transport, but you do not capture local heating that may be due to the VLF waves, which are not included in the model. Okay, so I will wrap up here then, maybe a few minutes early is always good for questions, and say that I've summarized some of the progress since the intermagnetosphere storms campaign in our understanding of outer zone electrons. And I have to say that it's been 15 years since the end of the campaign in 2006, and our tools are just extraordinarily evolved since then, both in terms of measurements and our computational tools. I neglected, because of time, to say anything about our advancements in our understanding of the inner zone protons. And there have been many advances in modeling and understanding the ring current and plasmasphere, which I've not had time to discuss. I will just get back to the fact that the plasmasphere is very important in determining the inner edge of the outer zone, as you see in this figure from Shinlin, and also certainly the ring current in terms of the strength of the magnetic field locally that's experienced by the radiation belt electrons and the adiabatic expansion of their drift orbits during strong ring current intervals and recovery. All of that should be taken into account by using adiabatic effects, by using phase space density rather than flux, which is something that we really came to do during the time beginning with and since the intermagnetosphere storms campaign. So finally, yeah, I wanted to comment that co-location with the plasma pause really doesn't necessarily sort out for us which of the two mechanisms in this cartoon are more responsible. I think we've concluded that both mechanisms are operative, and for some storms, one is dominant over the other. The plasma pause marks the transition from His loss to chorus acceleration. So it has been noted that we should really be ordering data by its location relative to the plasma pause if we want to understand this better. And it also serves as an obstacle to the inward propagation of ULF waves. The inner magnetosphere is a region of interacting 1 EV to multi-MeV plasma populations. And, because of this enormous range and the fact that one population affects the other, I mean, the radiation belt is kind of along for the ride, like cinnamon sprinkled on a cappuccino. But certainly we have to better understand the other two populations, I think, in order to improve our models of the radiation belts. So I'll stop there and take any questions.
Okay, thank you, Mary. So we've got a nice set of questions. I believe we have about 6 minutes to answer them in. So the first one we have is from Shannon Hill. Thank you for this talk. I would like to better understand the two mechanisms in Ma et al. 2016. I believe this is slide 17 in your presentation, radial diffusion and chorus waves. When you discuss radial diffusion, do you mean the radial diffusion of the plasma sheet electron population? If so, would this then cause chorus wave excitation in regions closer to the Earth? Or is the radial diffusion of the plasma sheet population also causing acceleration?
Well, so the radial diffusion models are typically describe the effect of ULF waves on the trapped electron population in the inner magnetosphere. And the periods of the ULF waves are comparable to the drift period of, say, 500 keV to multi-MeV electrons. Certainly, there are lower frequency waves that may affect plasma sheet energies, but you have to be thinking in terms of many drift periods of an electron interacting with ULF waves on a time scale such that their radial transport is slow, it occurs over many drift periods. So we don't generally think of radial diffusion acting on particles that are coming in from the plasma sheet.
Okay.
That's half the question. The other half is about the chorus acceleration, which again I could go on about that, and others could do better. Okay.
So we have a Adam, I might need to lean on you for a moment. We have a raised hand from Catherine. There we go. Catherine, do you want to ask a question?
Sorry, I must have put my hand up accidentally.
Oh.
I don't have a question.
Well, thank you for demonstrating how it works too. All right. Then I believe we have time for maybe one more live from Zheshen Chen. Great talk, Mary. May I ask what mechanisms lead to the observed 2-day time lag between ULF wave power and MEV electron flux?
Well, there the argument is the ULF waves, but correlation is not causation necessarily. So there are other processes operating during that 2-day time lag, including the local acceleration. But it was noted early on that there is this enhancement in power both for CME shock and high-speed stream-driven storms. And the example in the figure was for a recurring high-speed stream interval. And there the suggestion is the excitation of ULF waves are operating over 2 days to cause the inward radial transport and enhancement of the MEV electron flux.
Okay, nice and concise. Then I believe we have time for just one more. from Hsinju Connor. Thank you for the nice talk. Would you introduce any impact of radiation belt particles on the ionosphere thermosphere?
Well, certainly they're there. And that's a whole that's a whole other topic. So the MHD models, in fact, include first of all, the simplest one that was introduced is a precipitation of electrons that's proportional to the field-aligned current, which you can calculate from div j equals 0 in the equatorial plane of the MHD code. And that's a phenomenological precipitation model that is then used to calculate a conductivity variation so that the conductivity is not uniform in local time. And that's a boundary condition for MHD. And there are vast improvements to that now, including having the TI GCM in-car model for the ionosphere coupled to either LFM or to DEMERA and other MHD codes, wherein you have more than just a phenomenological representation of precipitation proportional to current, giving you a change in conductivity. So the system is coupled. There's absolutely no doubt about it. Excellent.
Okay, I want to remind everybody that these questions will be put over into Slack, and we can continue the discussion there. Adam, unless you cut me off now, I'm going to say we have time for exactly one more question. Okay, Anthony Chan has a good question here. Very enjoyable talk. Thank you, Mary. What are your thoughts on future directions for inner magnetosphere science at GEM and in general?
Wow, that's a big one. You know, there are two classes of missions that have just been so beneficial to better understanding or there are more than two, but two that came to mind that occurred since, during and since the campaign was the IMAG mission, which gave us an image of the evolving plasmasphere and ring current. And then the Van Allen probes, we sorely missed having an equatorial plane spacecraft associated with ISTP. So there were 22 years, roughly speaking, 2 solar cycles went by between the CRESS mission and Van Allen probes. And I'm very hopeful that we won't have to wait that long again, that with the development of CubeSats, that we will have more in situ measurements of all of these populations. But in addition, I think global imaging is due of different parts of the system, which really significantly improved our view of how the different populations interact. So that, and then the further development of models, I think we need to include, as Anthony knows in his work with Scott Elkington, the effects of local acceleration in some way into the MHD calculations. Yeah.
Excellent. Mm-hmm. Thank you very much, Mary. And that's it for that. So all of these questions will be put over into the Slack, and we'll continue talking about this there. Thank you, everybody, for your great questions. And I'll turn this back over to Adam.
All right, thank you, Aaron. So I'm going to move right over to our next two moderators. And so Hsinju and Nehpreet will be introducing our second speaker this morning. Thank you.
Hello, everyone. I am Nehpreet Walia, and I am 50th graduate student at the University of Tokyo. And I and Hsinju will be moderating the MPS tutorial session. And I'll be looking at the question and answer part, and she will introduce the speaker. Thank you.
Hi, everyone. I'm Hsinju Chen. I'm currently a rising second-year PhD student at the University of Illinois at Urbana-Champaign. And today I'll be introducing the speaker for MPS tutorial, Professor Jimmy Raeder. Professor Jimmy Raeder is a professor emeritus at the Space Science Center at Physics Department at the University of New Hampshire. He earned his PhD degree in geophysics at the University of Cologne and has been with UNH since 2003 after more than a decade of being a research geophysicist at UCLA. Dr. Raeder is the lead developer of Open Geospace General Circulation Model, OpenGGCM, a tool he originally developed as an MHD model of Earth's magnetosphere at UCLA in the early 1990s that can now be run at the Community Coordinated Modeling Center at NASA Goddard. He is active in the space physics community and served as the chair of GEM steering committee between 2006 and 2009, and has chaired and co-chaired multiple GEM subgroups. We're ecstatic to have Professor Jimmy Raeder here with us to give a tutorial on MPS today. Please welcome Dr. Raeder.
Well, thank you very much for the nice introduction. Also, thank you very much for inviting me. Greetings here from virtual Hawaii, make-believe Hawaii. So I'll give an overview of the magnetotail, a little bit different from what Mary presented. She was more like interested in the history and the latest developments. I'll talk about the GEM work on the tail in general, and then with some more personal comments on that. So, well, the magnetotail is a huge topic. I mean, well, tens of thousands, probably more 10,000 papers, you know, and often more opinions than attendees, you know, at this workshop. The tail was discovered in 1965 by Norman Ness with the IMP-1 spacecraft. That was the interplanetary monitoring.
Jimmy, just quickly, we don't see your screen, so please share.
Oh, I don't share
We're
my
still
screen.
looking at you, which is lovely. But
okay, sorry for that. Okay, forgot. Share screen. There we go. This and share. Okay, now I go back to view.
Wonderful.
Everybody sees it now? Okay. To slideshow. Here we are. So I talked about the just the title slide. I don't need to repeat that. So so this is the outline. So in '65, Norman Ness discovered the tail at about 30 RE out with the IMP-1 spacecraft, and there have been other observations of the tail that were sort of serendipitous, you know, by spacecraft that went to other planets, and the tail has actually been observed about 3,500 away from the Earth. So it's a very, very long thing. So in this talk, I don't have the time to go deep, but I'll try to be sort of comprehensive and convey the basic properties and the underlying physics. So that will be the magnetic field, how the plasma gets into the tail, why the tail is so hot. I mean, it's actually much hotter than it should be. How stuff in the tail moves around, where it ends up. And finally, I'll talk a little bit about substorms and the historical perspective. Of course, substorms by itself would be an entire tutorial talk. Well, not one, probably 10. So the magnetic field is really what defines the tail. So the classic picture is there's the lobes, there's a plasma sheet between the lobes, and there's a current sheet embedded in the plasma sheet. Now the classic model, so, I mean, in the 60s and 70s, they sort of came up with some current sheets to calculate the B mathematically. So there's the Olsen-Pfizer model and other models. One can do a little bit better. So one can actually take a description, mathematical description of the tail that is parameterized by a dozen or so parameters, and then use all the data that we have from the tail to make an optimal fit. And this has been the business of Tsiganenko, Nikolai Tsiganenko, for, well, about 5 decades. So he has about a dozen different models. Where he tries out all kinds of mathematical descriptions. You know, sometimes it's really prescribed current sheets and disks and whatnot. Sometimes it's more general polynomials. And these pictures here are cuts from his website. So he includes the dipole tilt. He can also include a shielding of the magnetosphere, magnetopause. And one can go even a step further, one can, because these are highly averaged models, of course. So these are data that were collected from many spacecraft over decades, you know, and if you mix that all together, you get a state of the tail that may actually never exist, you know. So it's just assume there are 2 different states of the tail, you know, and you average between the 2, you know, you get a state that doesn't exist. So these models are highly criticized, but they're also highly used. Why are they used so much? Because they're very convenient. Also, Tsiganenko, I mean, did one thing that few people do. He actually published the code. So you can actually get the code, I mean, to calculate the fields, makes that very easy. And as I said, one can improve that for certain events. Let's say you have, an event that lasts a few hours and you have some extra spacecraft here, you can improve the coefficients and get better representation of the field, and many people have done that. Now, one thing you'll find out is that when you calculate the magnetic field like that, it is actually not consistent with MHD, because MHD demands, at least as long as you assume a isotropic pressure, that the pressure is constant on field lines. And if you try to do that with this model, you find out that's not possible. So there's two types or two lines of work to improve that. One is by Bird, Schindler, and others, Michael Hesse, who basically solve a Grad-Schaffernov type equation to ensure that you get constant pressure. So that's actually the assumption, the ingoing assumption that the pressure is constant on field lines. And so there's a whole series of models, in 2D and in 3D from Joachim. Another way to deal with the problem is to solve it numerically. So you basically take the field as you have it, you dump in some plasma and then you iterate it until you get a equilibrium. But surprisingly, the models that you get then, or the representation of the field, don't look that much different, from an original Cyganenko model. Now, one thing you notice here is that everything is nice and smooth, but it is not so smooth, when you actually look at data. So if you start with the lobes, okay, they tend to be relatively smooth. Because they're very low plasma beta, so the magnetic forces dominate and they keep every field line as straight as possible. But there are transient perturbations there. They can come from the outside. So if a shock hits the Earth, you will definitely see it in the tail lobes. But there's also an intrinsic mechanism that creates variations in the lobes. So they were discovered somewhere in the 80s, I think. And Jim Slavin and Mark Molden worked on that a lot. So these are called TCRs, or transient, or traveling. Actually, that's the wrong word here, traveling compression regions. So what are they? They're basically, when you look at two hours here of cluster data in the lobe, so typical lobe field, mostly BX. Southern lobe, you have a negative field, minus 20, about 30 nanotesla, Y and Z is small. And then you see these little spikes here, and if you blow them up, you see that in BX, they're monopolar, and BY, BZ, they're usually more like dipolar excursions. The interpretation is pretty straightforward. You assume that there's a flux rope moving in the tail, in the plasma sheet, tailward, or earthward. There have also been observations of earthward moving TCRs. And it's sort of like a snake eating a rat, or a big anaconda in Florida eating an alligator. So as it goes down the tail, it sort of bulges out the tail lobes, and creates that signature. So it's relatively easy to understand. Okay, so that's the lobes. What about the plasma sheet? Now, the plasma sheet is most of the time kind of a mess. You see variations there where the delta B over B is approximately 1. So we would call that turbulent, right? Okay, so because when you look at the frequencies here on the right, the spectral density, it looks pretty much like a turbulent spectrum. But there is some peculiarities about that kind of turbulence. Typically you find turbulence or study turbulence easily in the solar wind, which is very convenient because the solar wind comes blowing by at you at vast magnetosonic speeds, so you basically really measure not the time variation, you measure the K vectors. And the tail is not so easy. Now, the complications here arise from the fact that first of all, we don't know what it really is. And I'll come back to that later. The turbulent eddies that you would have in hydrodynamic turbulence, where plasma is really circling around in eddies, they're somewhat depressed or suppressed because there's a magnetic field. The magnetic field gets twisted up and tries to restore them. So that changes characteristic. It's highly dependent on the plasma beta, but the plasma beta in the plasma sheet is often of the order of 1, so the magnetic forces really matter. The second peculiarity is that the turbulence is confined to a box. So here's a cartoon from Joe Borofsky and Herb Hudson, so where they actually draw the lines, the field lines in the plasma sheet, as a tangled mess, and that's probably what it is. But it also shows you that in the Z direction, you only have about 3 RE or so, and in the X direction, well, they're longer, but that limits the number of K vectors that actually fit in here. So that's the turbulence in a box, but it's more complicated than that because the field lines are also connected to the ionosphere. So at the ionosphere end, so if the turbulence is alphenic, these alphenic waves will actually go to the ionosphere and most of it will bounce back. So that will also create a boundary condition that is somewhat unusual for turbulence. So it's not quite comparable with what you see in the solar wind. So now in the tail, it's also not so easy to translate the time measurements because that's all we have. I mean, all we have is time series, but what you really want to know is the K spectrum. So you can make some assumption here. Two extreme assumptions are, one is that plasma is actually frozen in. In that case, you use the local flow speed, to translate the time variation into spatial variation, or you can assume that it's alphenic. Okay, so these are all waves. I mean, in this case, you get something quite different because the alphane speed is much different from the flow speed. So what you see here that you get wavelengths. So this is expressed in types of wavelengths. I mean, up to 10 RE or so, but there is some at about 1 RE or 1 and some RE. There's somewhat of a turnover of the spectral index, which indicates the presence of the box, the box thing. Okay, and then of course at very long wavelengths, you don't have anything. So the question then is, I mean, and that's still open for, very few people actually studied this, is the nature of the turbulence. Are these really eddies, or are they waves, or a mixture of both, or are different conditions under which you have one or the other? If it's waves, what kind of waves? Alphane waves, slow mode, magnetosonic. Then there's the question, what drives the whole thing? Why is it turbulent? Why doesn't it slow down, and then eventually die out and become very laminar? There is flow shear, and I'll show that later on, that the Birstibug flows. They may create Cohen-Helmholtz instabilities. There are other MHD instabilities like ballooning, kink mode, and things like that. There is, if it's not quite MHD, if it is anisotropic, you might have the fire hose instability, the mirror mode instability. And of course, you can have all kinds of kinetic instabilities, whole books about that, There was also a theory at some point, from Iowa, by Chris Gertz, saying there's a direct driving from the solar wind, but I think that has pretty much been ruled out. So then there's the question of the consequences. So normally the plasma in the tail, like almost everywhere in the magnetosphere, is collisionless. So the collision time between two particles is of the order of a day or so, Well, when you get these waves, especially at a higher frequency, you create an anomalous diffusion. So you get transport. You get also anomalous viscosity, also called Taylor viscosity, and anomalous resistivity. Ultimately, this leads to mixing of the plasma. There's also a theory that was proposed a long time ago by some Russians, like Zelyeny, of tangled field lines that create chaotic particle orbits, and that's called percolation. Like the coffee percolating through your coffee filter, So that is also an effect that one can actually calculate, and one can also look at the particles, and if the type of the turbulence is correct, you might even get particle acceleration out of it. Then finally, not finally, but there is also the question of what happens to all that energy that is actually in that turbulence, So almost certainly there is some kinetic dissipation at small scales, like it's in the solar wind probably. There's certainly some energy dumped into the ionosphere. So if you have alphane waves traveling towards the ionosphere, as I said, most of it getting reflected, probably about 90%, but some of it actually goes into the ionosphere. Some of it accelerates particles. As the alphane waves steepen up closer to the Earth and become kinetic alphane waves, accelerate particles and create aurora. There's certainly a lot of energy going, or most of it is probably going out of the tail. It's just in hydrodynamics, you would call that vortex shedding. That's what you have at the end of an airplane. And ultimately, there's also some of the energy injected into the inner magnetosphere and creating all what Mary just talked about. About the radiation belts. And the ring current. And I'll come back to that in a minute. So it's definitely not classical homogeneous turbulence. So there's a lot of work to be done. And I will repeat this statement many times here. Much work to do, and 100+ constellation satellites would surely help. Because if we had a satellite constellation like that, we would probably be able to distinguish between eddies and waves, for example. Now, how does the plasma get in? So there's one source that is sort of obvious, is the ionosphere. So there is a polar wind, has been observed for a long time, and also a thing called the cusp ion fountain. So these are really particles coming out of the ionosphere. Now, when it comes to hydrogen or protons, you can never distinguish them from solar wind. I mean, virtually impossible. I mean, maybe by their distribution. But what comes out of the ionosphere is mostly oxygen. And then there's also the helium or alpha particles. There's the helium-3 that comes from the Earth, and there's the helium-4 or the alphas that come from the sun. So that ratio can also be used as a tracer. Now, this has been done for a few decades now. I mean, since I think Ed Shelley in the 80s had their first spectrometers. Cluster has a spectrometer, and pretty much, well, Themis does not have a spectrometer, but MMS has spectrometers, so we know quite a bit about that now. Most of the time, when you look at the ratio of the density ratio of O+ to H+, it's very small. It's a few percent, you know, when it's quiet, but it definitely increases when the geomagnetic activity increases. So can become 1% or even larger. So in other words, it becomes dominating. Oxygen can become the dominating species. There's also, although this was already taken, I mean, there's a dependence, a very strong dependence on the solar irradiation, or the F10.7 flux, or the UV flux, which basically produces the O+, I mean, in the ionosphere for the most part, you know. So when F10.7, so during solar maximum, you have about an order of magnitude more than during solar minimum. But this year, this picture is actually solar max, so near solar max. So it's about as high as it gets. Now that's one source. The other source is the magnetosphere itself, or the solar wind. So it can reconnection at the day side, opens up field lines, produces a low latitude boundary layer, also a high latitude boundary layer. So basically what happens is that the field lines loaded up with solar wind plasma convect over the cusp and sink into the lobe. So in MHD terms, this is a slow mode expansion fan that was treated by George Sisco a long time ago. Then the idea is that the plasma eventually reaches the plasma sheet and convects earthward. And so this makes what we call the hot and tenuous plasma sheet, which is typically a few keV and about a 1 per cc or smaller. So a tenth of a cc is also typical for the plasma sheet. But as I will show later, this is a very, very strong simplification here, that everything is nice and two-dimensional, because that's not how the tail is. So first of all, the IMF rarely is pure south, you know, so it's usually tilted, I mean, east-west more, you know, so instead of blowing the plasma in over the cusps, you know, it probably rather comes from the sides more. And there's probably also no such thing as a stationary distant X line, you know. So for a long time, people believed there was around 80 RE or so, there was 60 RE, there was an X line, you know, that was just stationary during quiet times, you know. I think there's lots of evidence that shows that that is not the case. Okay, and then occasionally you get something that is called the cold dense plasma sheet, or CDPS. So during northward IMF, the plasma sheets get colder and denser. And here on the right side in that figure, so forget the simulation, the black line is cluster data. It's almost a day worth of data here. And you see first, the first few hours, you see the typical very tenuous and hot plasma sheet. And I think at times, this is always plasma sheet. It goes into the boundary layer back and forth, so it becomes a little colder, but then eventually becomes quite cold, you know. So then it really goes down to about a keV and not more or below a keV. Density goes up to 1 per cc or higher, and also quiets down, so you don't see much flow anymore. So we did simulations of that, so we could actually reproduce that quite well. The figures are all from a wing paper, from a review paper here. So what this was done by my graduate student a long time ago. And so, yeah, and of course in the simulation, go back. In the simulation, you can actually trace plasma. So that's what we did here. So OpenGCM simulation of one of these events, actually exactly of these events. So you take a plasma parcel in the tail where you see it, you know, I mean, where it's cold, you know, and you trace it backwards, you know, and then you look at all the field lines attached to that. And you see it starts out as open field lines in the solar wind. They slowly convect in, they reach the magnetopause. And if you look very carefully here, you'll see that it first reconnects on one side and then it reconnects on the other side, becomes a closed field line, and then it convects further tailward along the flanks and eventually sinks into the plasma sheet and of course carries that cold plasma with it, you know. It actually doesn't stay that cold, you know, the magnetosheath plasma is still colder. That's about 100, 150 EV. And that goes up to about almost a keV when it gets in the tail. Not quite sure yet why that is so. I mean, part of it is No, it cannot be adiabatic. It's a non-adiabatic process. Now, a competing theory says, well, it could also be Kelvin-Helmholtz waves, so Dave Siebeck talked about that, I think on Tuesday, about Kelvin-Helmholtz waves. So they can also create some mixing of the plasma on the boundary, but then still you have the problem to get the plasma deep into the plasma sheet, so which requires then some other process, so I don't think that gives you really a complete picture, the mixing here. And another theory that is probably not quite true, is simple diffusion, but the diffusion coefficients are so low that's hard to believe. So now, why is the tail so hot? So, first of all, let's see how hot it is. Okay, so this goes back to, from Borofsky showed this first. Joe Borofsky had a VGEM meeting, surprise, surprise, in 2006. And he looked at the specific entropy of plasma inside and outside of the magnetosphere. So the solar wind is very cool and fairly dense. So typical solar wind, canonical value is 10 per cc and just a few EV of temperature. And so on this diagram, it's not even drawn. It would rather be where the less dense text is, all the way down here. So now the plot is log of the density versus, or the temperature versus the density, so if stuff is adiabatic, it would move along these adiabats. We have lines of constant specific entropy. So from the solar wind to the magnetosheath, it gets heated. Obviously, and that is clear why. We know that shocks, produce entropy. There's no secret to that. Now, if you look at the low latitude boundary layer, it has been heated a little bit. But when you look at the upper left, that is the plasma sheet. Okay, so Joe separated that into the distant plasma sheet, mid-tail plasma sheet, and near-Earth plasma sheet, where near-Earth, I believe, is mostly data from the Lanel spacecraft, so it's really at 6.6 Earth radii. And you see it's orders of magnitude, the entropy is orders of magnitude higher. And on the other hand, once it is in the tail, when plasma comes, let's say, from the distant plasma sheet all the way to geosynchronous, it pretty much slides along the adiabats, so it doesn't get heated by dissipation anymore. So it gets hotter, yeah, it gets hotter, but it also gets denser. So it's simple adiabatic compression. You can view that as a conservation of the magnetic moment, and along also Fermi acceleration along the field line for the parallel part. So that's easy to understand. And the near-Earth cold dense plasma sheet and distant mid-tail cold dense plasma sheet, that lies somewhat in between, which would be understandable because the plasma that comes in is already colder than the other plasma. But still, there's a question, why the hell is that so? So I redid this a few years ago with newer data. So I took MMS and Themis data and separated then a magnetosheath and plasma sheet, and I basically got the same results. All the blue here, blue stuff is magnetosheath, red stuff is plasma sheet. There's a little bit more overlap here, and there's a little bit more scatter. There's a possibility to misidentify the regions because it's probably not a good idea to use the density and temperature to identify the regions, but you don't get around that ultimately, because it's sort of a circular argument possibly. But still, it basically confirms the results that Joe showed. And the question is why? So because we have more data now, so I looked a little bit into dependency on parameters. So yeah, what does it depend on? So I looked at the geomagnetic activity. So I looked at from Omni, the L index, so the substorm index, and the SIM-H, the storm index. And of course, you get a gigantic cloud here. Most of the time LL is near 0. And what you would expect is that AL decreases or increases in absolute value, that the entropy, which is the y-axis here, the log of the entropy, would actually increase, but that's not true. It actually goes down. Now for storms, so these red bars here are the median values, for each of the bins. Same if you do the SIM-H, up to about -50 is, well, you could still argue it's more or less constant, but then for higher SIM-H, it falls off. So is there something in the solar wind that does it? So I looked at all kinds of parameters, and the only ones that stood out, and the obvious one you would look at is the IMFBZ, right? That drives activity. But very counterintuitive. As IMFBZ gets more negative, actually the entropy in the tail decreases. It also decreases when it gets more positive, when you get very strong positive field. I mean, that sort of makes sense, I mean, with a CDPS, but the other one does not make sense. Now, what really drives is V times BS, or the electric field in a solar wind, the southward component of the electric field, or one could probably go more fancy, I mean, and use one of Pat Newell's coupling parameters or so, but I don't think that would change the picture very much. And again, the same picture. As the driving increases, the entropy in the tail actually goes lower. And so why is that so? Well, you have to think about what does the heating. So the energy conversion in MHD can be written as E dot J, that's out of Jackson. There's no assumption whatsoever in there about plasma or particle populations, but in an MHD plasma, the E is minus V cross B. You dot that with J, you might add a resistive term. Okay, so it becomes minus V cross B plus A dot J, and you do a little juggling with the vectors. So you get E dot J is V dot J cross B plus A dot J squared. Now the V dot J cross B, that's the velocity times the J cross B force. So that is a rate of work. That's the work being done by the plasma on the field, or the other way around. Can have either sign. So that is adiabatic. But the last term here, A dot J squared, is always positive. So that means this is really where dissipation comes from. That's or what we call the ohmic dissipation. Okay, so now we tried to calculate that from MHD code. So, well, you have to be careful there. There's basically two electric fields in an MHD code. I mean, one is the simple motion electric field, minus V cross B. You can always calculate that. And the second is the numerically calculated field, which I call N here, that includes all kinds of other errors, resistive terms, upwinding, flux limiters, and all the methods to keep the numerical scheme stable. So they all act effectively as a resistivity. So that means that the true dissipation in the code can be extracted uses the difference of the two fields. You can look at En, the numerical electric field minus the motion electric field, dot that with J. That should give you the dissipation. There's some subtleties involved because these fields are not necessarily defined on the same grid. So here is a movie of some event, and before I even launch that, I will tell you what it shows. Okay, so on the upper left, this is the magnetic field Z component, the northward component, in the in the center of the current sheet. So you can actually find the center of the current sheet for every grid point, and then you can look at the Z component of magnetic field, and you can project that, on the XY plane. So the Earth is roughly on the left here in the color bar, so where the 0 is, and then you get X, about 35 RE down the tail, and Y into the flanks plus minus 15 RE. So this is the Z component. Obviously, as you get closer to Earth, it becomes much stronger because you get into the dipolar region. The second on the top is the velocity. It's only the X component of the velocity, and red is earthward and blue is tailward. And obviously where red meets blue, that is usually where you have reconnection happening. That's where the X line is. You see a very ragged zigzag X line or multiple X lines here. The top right is the entropy, and it actually will not really tell you that much because the entropy has many different sources. It's different plasma coming in from the solar wind, so that has already different entropy to start with. Now the bottom is the interesting part. On the left side, that is the E dot J, which is the motional electric field. That's the total field. That includes the numerical terms, the resistive terms. The middle is the ideal field, and the right is the difference. Okay, so you see the difference is much smaller, and the difference basically indicates the heating rate. Okay, so if I let that run now, you will see a lot of things, and this turns over again and again. So first on the left, top left, in the in the BZ, you see these ridges of high BZ moving towards the Earth. Those are dipolarization fronts. And that's very clear. On the right, you see the flows that are the BBFs. Whenever it's red and going towards the Earth, those would be identified as a bursty bulk flow if a spacecraft sees them. So they come close to the Earth. Some of them penetrate. They slow down as they get close to the Earth. You see virtually, I mean, on this scale here, on this color scale, you will not see anything penetrating closer than 10 RE. But I can tell you they actually do penetrate closer than 10 RE. I mean, and it's also true for the dipolarization fronts. You see a slow rising of the entropy, but that is probably due to other things. You know, it's probably due to plasma coming in that has high entropy already. So the heating, you can see in the top right, you know, that's basically the numerical heating, and you see red and you see blue. So which means there's also some numerical cooling and there's some numerical heating. So one would expect, you know, and it has been studied now with MMS quite intensely, you know, that heating occurs wherever you have X lines. But that's really not what you find, you know. I mean, what we not find and don't find really in the simulation. There is no dissipation. And I need to say a word here about dissipation. You know, heating and dissipation is not the same thing. Okay, dissipation is really irreversible. Okay, so that's the eta J squared term, you know. And whereas heating, you know, I mean, can just be compression, you know, that heats it up. Okay, so I don't have that much time, so I will move on. Now, people can then argue, you know, well, the full Ohm's law does not may change all that, but I mean, you can use the Ohm's law, I mean, with all the terms in there, I mean, the fluid Ohm's law, you still get the same, you know, you get one term that is irreversible, eta J squared, which basically it contains all the collisions, you know, and all the other terms are just work terms. You know, you have the plasma doing work against the electron pressure, you have plasma doing work against the ion pressure, you have plasma doing work against inertial forces, you know, so that doesn't really change it. You can go a step further and use Boltzmann equation and you still end up with the same result. There is a possibility that shocks in the tail, slow mode shocks associated with the reconnection process, I mean, they're rarely observed, but they may be there, that they could produce the entropy. But Antonius Otto showed that there, I mean, also in this review paper, that they're for prevailing parameters in the tail, they can hardly produce any entropy. So this is an open question, okay? And so I would like to summarize this as a hypothesis, I mean, the observations, and basically say this, I'm doing quite moderately times, the plasma sheet acts like a slow cooker, you know, so it's constantly churning and slowly dissipating energy. There's not much plasma going out and not much plasma going in. But then this may be electromagnetic power, energy dissipation, could be Kelman-Helmholtz wave, some sort of viscous interaction, and the end of the turbulent cascade. But then when things become active, basically what happens is the tail rids itself of that extra internal energy by just throwing out these plasmoids and tailward PBFs, and also by injecting some of the low entropy plasma into the inner magnetosphere, and ultimately convecting it out on the day side. Okay, so that would explain that during active times, the entropy actually goes down in the tail, the specific entropy. Okay. Should also say a word here. I mean, this is often confused, you know, entropy, I mean, dissipation, you know, and heating. So a lot of MMS papers. And again, a constellation with 100+ probes would really help to nail that down. Come back to that in a minute. Okay. The plasma sheet is inherently 3D. I don't really have to tell you this anymore. So this is on the upper right. This is a picture by Ed Hones from 1985. Showing how the nearest neutral line of substorms works. Okay, so it's an inherently two-dimensional picture, assumes that everything is more or less constant in the y direction. Okay, now the global simulations, and I'm not the only one who's shown that, you know, I've seen Slava Merkin and John Lyon show this with the Gamera code and other codes. They always show the same thing. You know, you get these BBFs, you know, you get these snake-like flows in the tail, you know, it's highly three-dimensional, you know, there's no question about it. And the observations that we now have with MMS and with Themis, you know, they really confirm that. So, I mean, all these observations, all these simulations are actually quite consistent with the observations. Okay. So now years ago, we have already proposed, that goes back into the 90s, there was a NASA working group, I mean, science definition team for constellation missions, you know, that actually proposed something like 100 satellites. And that was more than 20 years ago. And it could answer so many questions, you know, how many BBFs are there in depolarization fronts, what's their size? I mean, I forgot to say where they're moving, how they're moving, their structure, their dependence on the geophysical condition. There are these wedges and wedgelets, that connect the magnetosphere to the ionosphere. Have been discussed lately a lot, I mean, and they're of course related to the BBFs, There's a question, is a substorm just one big BBF, is it something else, So this was already conceived a long time ago. And so we did some studies, I mean, putting virtual satellites into magnetosphere and then try to figure out, how do we space the satellites, to get optimal results. Should always read that. Finally, where does the plasma go? Most of it just blows out the back of the tail. Some of it gets injected into the inner magnetosphere, but that's not an easy path. The plasma must have low entropy. This was established some 20-something years ago at the beginning of GEM, actually, by the Rice group for the most part, by Gary Erickson and Dick Wolf, that there has to be low entropy, otherwise the plasma doesn't get in. And they named those bubbles, and they have to break the barriers basically of the inner magnetosphere to get close enough in, to contribute to the ring curve. And these bubbles eventually slow down and get embedded. So Kramer did a simulation with OpenGCM a few years ago, that shows that here, this is an interesting diagram. It's time on the x-axis, MLT on the y-axis. It's just taking parameters at 10 RE down tail. The colors are the flows. So those are the BBFs, the high-speed flows, and the little dots are minima. Yeah, minima of the the minima of the entropy. So, and you see they're very closely follow each other, and you can do that at different distances, and you see that eventually these BBFs slow down, on average. So this is for lots of different events. For one is the quiet event, that's these dotted line at the bottom here, eventually they slow down, but you can still trace them down all the way to 4 RE. Okay. Now I want to give a little history. I hope I still have 5 minutes for that. So at the beginning, as was already said by Bill Lotko and Mary in the previous talk, we had campaigns. One was the tailed substorm campaign, and back in those days, text was actually written on paper. And so a memorable contribution came from Chris Russell. So this is this little brochure that I found in my shelf. We'll not go through details here. So Chris basically explains the near-Earth neutral line in terms of magnetic flux, day-side reconnection, growth phase, adds to the lobe, use the transport rate. Eventually you get night-side reconnection, pushes it inward, and the recovery brings it all back. And this ultimately led to what was called the 2-minute problem of substorms, which Vasilis Angelopoulos used in a brilliant way, to sell the Themis mission to NASA. So the idea is simply, is it first reconnection happening in the tail that makes the plasma sheet move earthward and then cause an auroral breakup? Or is it something close in the tail, that first happens, cause an auroral breakup, that ultimately causes reconnection in the tail? It's the inside out, outside in versus the inside out scenario, So, and when you look at, people have tried to solve that by timing different substorm signatures, and this is from a paper by Meng and Leo. So they tied everything to the auroral breakup, and then they found all these other signatures like fast flow deporization, injection, PI2s, AKR, auroral kilometric radiation, for those who don't know that. And well, they all occur earlier, but it's hard to tell which one is actually the earliest and which one is the latest. So, and you see these large arrow bars here on this, So, and Chris had an opinion on that too. So a regular series of meetings maintains the appearance of progress, but it does not always signal the existence of real progress. It is commendable that the substorm community wishes to converse as often as they do about the work on the substorm problem, and has established a biennial international substorm conference on top of all the other meetings in the field that treat substorms. But a skeptic might also view this as evidence that the community is more interested in traveling than in working, especially since the same ideas about the substorm process are being debated today as they were being debated 20 years ago. One cynic, guess who, has even suggested a conspiracy theory of substorms that the principals have agreed not to solve the problem in order to keep the field alive. Okay. Well, many of these meetings have happened since then. And of course, At GEM, there was always discussions about substorms. Okay. Now the good news is, a few years later, Bob Stranger and we actually solved the 2-minute problem during the poster session, and we were very happy. You know, look at Bob here, 2 drinks in his hands. You know, so well, it was a little problem though. We were planning to make the announcement the next day in the plenary session, you know, to tell everybody what the solution was, but unfortunately, we drank too much, and we have forgotten what the solution was by then. That's sad, right? So, but there's some hope. There's some hope. I talked to a psychologist, and he said, well, if the exact circumstances of the memory loss can be recreated, there is a 50-50 chance that the lost memory can be recovered. So we would solve that problem. So for the sake of science, Jem, please, let's go back to snowmass and, well, obviously reenact it. Okay, thank you. That's all I had to say for today. Too bad I cannot hear the reactions. The yelling. Okay, I'm done. I think I should unshare now. Is that true? And I stop
Thank
sharing.
you so much, Jimmy, for a very enjoyable talk. 100 plus slides would definitely help. So let's move on to the question and answer section. And there are 5 questions right now. And the number 1 upvoted question is by Larry Kapko. And this discussion of why the PS is so hot implicitly assumes that the solar wind is the source of plasma. What is the current consensus on what fraction of PS plasma is solar wind in origin versus ionospheric in origin?
Well, I think I showed that, right? I mean, there is the work by Kissler and others, you know, have looked at the plasma sheet for a long time. And we have these tracers, so we know most of the time it is a minor constituents. The other thing that matters here is also that the ionosphere plasma is also very hot. I think it's probably even more difficult to make plasma flowing out from the ionosphere, which is typically only 100 eV or so, you know, I mean, actually up to a few kV. I mean, what would heat that? You know, I wouldn't know that. And there's long been a discussion, and I don't know where it stands right now, whether the outflow from the ionosphere goes directly close to the Earth, you know, into geosynchronous or maybe 8 RE or so, and gets heated there, or whether it actually goes out much further first, you know, to 20 or 30 RE, you know, and then gets mixed up and heated and then convected inwards, you know. So I think that's an open question. And again, the 100 satellites might help with that, you know. So.
Okay, so I'll move on to the next question. It's by an anonymous attendee. On alphanic energy deposition at low altitude from PS turbulence, BBFs and dipolarizations in the plasma sheet, low altitude statistical distribution of the alphanic pointing flux, for example, in Keeling et al. 2003, Chaston and Hatch, exhibits intense pointing flux in the night side sector, but little flux in the dawn dust sectors, which connect to magnetospheric flanks where intense KH activity is observed. Do we know why intense alphanic waves originating in the PS make it to the ionosphere, but not those originating on the flanks?
Oops. Okay, so there was a question at the end. Well, I didn't really touch that subject very much because it really is, in my opinion, belongs to MI coupling. Well, I mean, we would need the 100 satellites to figure out, I mean, where are the alphane waves really prevalent? You know, I mean, if the alphane waves are much more prevalent in the center of the plasma sheet, which they probably are, than in the dawn and dusk flanks, you know, that would explain why there is pointing flux, I mean, coming down, I mean, from the center of the plasma sheet, you know, than from dawn and dusk, you know. The thing is, I mean, there's very, very few studies have been possible to actually link things between the ionosphere and the plasma sheet, you know, because you have to be very lucky. You have to have some images. You have to have the observations in the ionosphere at the right place, but you also have to have them at the right place in the tail, you know, and the tail is actually where you most of the time don't have them in the right place. You know, ionosphere, you got some imaging, you know, which covers a larger area, but in the tail you don't, you know. So there's some studies by F.T. Zester, there's More lately, I think Nishimura and company, have tried, to tie things together, and my student, Vashi Fadusi, she's talking tomorrow actually, has also tried to tie that together, so we have a paper coming out, but it's right, observationally, it's a very difficult thing to do because you have these very, very few conjunctions. Look, we also don't have an oral imager right now. We have ground-based alt-sky imagers, but they're very limited, the area they cover, and they're limited by the weather, if there's a cloudy measure, nothing. And so it's difficult to do right now. So fortunately, in a couple of years or 3 years, we will have SMILE. SMILE has imager, has UV imager. So we hopefully get back at least to the state that we had with image and with polar, So, it should be better. It should be possible these days to have imagers that are much better than what was flown 30 years ago or 20 years ago, but there's no dedicated funding for that, So the SMILE imager is a secondary payload only, The primary payload is the neutral imaging of the X-rays, right? The X-ray imaging. Okay, that's all I can say right now.
So we have many questions, but we only have time for one question and a short answer, sorry. So
okay.
Magnetotail plasma is fully collisionless. The corresponding Vlasov equations conserves the entropy. How can one define dissipation in the magnetosphere beyond the numerical dissipation in the MHD models?
Okay, so in the models, I can hide myself and say it's numerical somehow. Of course, in nature, not. It's a simple effect, that the entropy is so high. I don't know the answer. I put a few things on my slide, that might contribute to the answer. But what I can say is, and that actually goes to the next GEM meeting, where we should have joint sessions with the solar folks, because they have exactly the same problem. The corona is way too hot. The entropy of the corona is way much than it should be. The boundary condition of the corona is ice cold, basically, the photosphere, yet the corona is so hot. Very similar to what we have. So the processes are probably similar too. And they haven't figured it out yet. We haven't figured it out yet. The solar people are taking a good stab right now with Solar Probe, and so they're trying to get as close as possible, to get more information. And I think our community and their community really need to exchange notes, and next year in Hawaii, that would be a perfect place to do it.
Okay, thank you. So I'll close the question answer session, and we will post these questions on the Slack, and we can continue the discussion.
Okay, so I will try to answer them on the Slack, within the next week or so.
Yeah, so yeah, Adam, please go ahead. Thank you.
Thank you,
Okay,
Nehpreet.
thank you. Thank you, everybody.
And thanks, thanks, Jimmy. Thanks, Mary. Please join us on the Slack to thank our speakers more. There's a great conversation going on over there already. I'm just going to share my screen. We have a couple of announcements and a couple of summaries, and so I'll try to go through this as quickly as possible. So on Tuesday evening, we had the Sam Bingham Community Cares Initiative mental health session, and there are a lot of results from that we wanted to share with the entire GEM meeting. And so a couple of takeaways. The poll results will be posted on the VGEM website, where we're almost finished putting that together, and we'll share that link via the Slack. But just a couple of takeaways from the quiz. And so we found that the risk of psychiatric disorders was higher in academia than in the other highly educated groups. And so 68% of the people that attended guessed this correctly. So it's certainly something that we seem to be aware of in our field. We wanted to make sure that everybody was brought up to speed. In academic settings, approximately what percentage of undergraduates and graduate students suffer from anxiety and depression? The answer was 15%, but of the survey, the people that guessed, most participants guessed around 30%. So they said it's around about double that. And one of the other questions that we had was, and this was based on a 2014 survey. So one of the other questions that we had was that in polls of faculty members and graduate students, the number of reports of mental health issues during the pandemic has increased by how much? Most people guessed around 50%, but in several published Nature papers, it's actually been shown to be around 100%. So this is just a message to everybody out there that this is a real issue in our community. A lot of people are suffering from this, and it certainly has increased during the pandemic. And so the message we wanted to give is to take action. And so there are online training materials, and Chris has posted something on the Slack in the channel. So please take a look at that. Also look at Dr. McMillan's presentation. You can download that and she offered some information to contact her to ask for any additional information. And basically everybody just helped try to break the myths and remove the stigma. And you might have seen in the news yesterday that Simone Biles, a famous gymnast, has pulled out of the Olympics because of mental health issues. And so we really wanted to join everyone else in applauding her for being brave enough to do that to protect her mental health. And so another thing that we want to bring up was the gym logo. So you may have seen the messenger last night. And so we put together, we had 17 submissions and we narrowed them down to 3 along with the original gym logo. And so please cast your vote on your favorite concept and you'll be automatically entered into the running to win a $25 gift card. And you can find this on the VGEM website or in the Gather Town in the lobby. And the deadline to vote is today at 6 p.m. Eastern time. So we'll be announcing the winner tomorrow morning. And just finally, get over to Gather Town now. So you can find the link on the VGEM website. The icon looks like this. Check out the photo gallery in the lobby. Check out the 3D printed magnetosphere model, which I believe will be running during the poster session again. And also the Mountain Dragon, which is something new in the lounge. So have a great day, everybody, and thanks for your attention.